Hello everyone and welcome back to the NIIT YouTube channel. At NIIT we believe that real learning happens when you don't just watch code being written, but you understand how real systems are designed, structured and engineered. In today's session we are going to explore something exciting and practical. So we are going to build and deeply understand a complete Pacman game using JavaScript and the HTML5 Canvas, but this is not going to be a typical type along tutorial. Instead, we will use a professional engineering approach known as reverse engineering. That means, first, I will show you the final working system, and then step by step, we will dismantle it conceptually and understand how every part of the system works logically, visually, and programmatically. And by the end of this video, you will understand how the canvas rendering system works, how a game loop is designed, how grid based worlds are built, and how collision detection is implemented, how artificial intelligence is written for enemies, and how professional UI states like start screen and game over overlays are managed. So, this is not just about building a game, this is about understanding how interactive systems are engineered. So let's begin with the final result. So this is my game right here. So I've just opened up my pacman.html file. We will get through it. So I will just press space to start, and as soon as I do that, my game starts, and the user has 3 lives. And if when the Pac-Man eats the food, the score gets incremented. So let me just sacrifice all of my lives, so I could show you the output of my end screen. And here we go. So after the user has sacrificed all of their lives, um, it will display a message that the game is over, and the user could either press R to restart, or if the user doesn't want to continue, he or she could press Q to quit. So what if I want to restart the game? So I'm just gonna press R, and it will take me back to the start screen page. Now, this is the final system, and this is actually the Pac-Man game that we are about to analyze and understand. So you can see a custom start screen. Then you also have a smooth player movement. You have grid-based navigation, food collection with scoring, enemy ghosts that intelligently move through the maze, a life system, and a game over screen with restart and quit options. So everything you see on the screen is controlled by JavaScript, and there are no buttons, no HTML layouts, no external game engines. The entire world is rendered manually using the HTML5 canvas. So now that you have seen the final system, let's go behind the scenes and understand how this is built from the ground up. So before we look at any code, we must understand the architecture of this project. So this game is divided into 4 major components. So first you have pacman.html. So this is the entry point that creates the canvas and it loads the asset. Second, you have game.js, which is the core engine that controls the game loop, state, UI, and orchestration. Third, you have pacman.js, which is the player module responsible for movement, animation, collisions, and scoring. And ghost.js is the enemy module, which is responsible for again movement, pathfinding, and artificial intelligence. So this structure follows an important software engineering principle known as separation of concerns. So each file has a single responsibility. HTML would handle the structure, game.js would handle the system flow, pacman.js would handle the player behavior, and ghost.js would handle the enemy behavior. So this is how real world applications are architected: clean, modular, and scalable. So now let's go file by file, starting with the foundation, which is the HTML file. So I'll just click on pacman.html. So this is a standard HTML document, but unlike traditional websites, this page does not display content using divs, button, or layout. So instead, it hosts a canvas, which is a drawing surface that JavaScript can control pixel by pixel. This means every wall, character, animation, and the UI element is drawn manually by code. So you can see this over here, which is canvas id is equal to canvas, width is equal to 500, height is equal to 500 canvas. So this line, this particular line, it creates the entire game world. The canvas is essentially a blank digital whiteboard, and by default, it would show nothing. JavaScript must explicitly draw every object you see, and the width and the height define the resolution of the game area. All rendering calculations like movement, collisions, positions are based on this particular coordinate system. So I'll just show you in my final output what this actually is. So this is the height of my game and this is the width of my game. Right now it's set to 500, but you guys can increase it manually if you want to. And it could be 1000 or 1200, that's totally up to you. Now we will discuss this block, which is basically an image asset preloading. So these hidden image elements load the sprite sheet for Pacman and the ghost. So although these images are not displayed directly in the browser, they are stored in the memory. JavaScript later extracts individual frames from these images and paints them into the canvas. So this is a common technique in a 2D game development known as sprite rendering. So I'll show you the images. So you have animations.gif and ghost.png. So this is my pack and ghost.png. These are my ghosts that I have. So I hope you have an idea about this now. And now about this. This is my script loading order. So the order of these files are critical. We load Ghost.js and Pacman.js first because they define classes. And after that, we load game.js, which creates objects using those classes. And if this order were reversed, the browser would fail because it would attempt to use classes that have not yet been defined. So this demonstrates how dependency management works in modular JavaScript systems, and with the HTML in place, let's move on to the game engine. So now I'm gonna click on my game.js, which is again basically the core engine of this whole Pacman game. So first let's just discuss these two lines. Here the JavaScript it connects to the canvas element and the canvas context object is our rendering engine. It provides drawing commands such as rectangles, images, text, transformations and color fills. So everything that appears visually in this game is drawn through this context. Now about this is our drawing helper function. So this helper function, it simplifies drawing rectangles. So rather than repeatedly writing multiple drawing instructions, we define a reusable abstraction. And this demonstrates a core programming concept, which is code reuse and abstraction. So we will use this function to draw walls, food pellets, background and UI panels. Now these are your direction constants, and as you can see we have specified direction right as 4, direction up as 3. So these constants represent the movement direction. So instead of using raw numbers like 1 2 3 throughout the code, we give them a meaningful name. So it would improve the user readability, it would also reduce the logical error and makes the system easier to extend later. That's your game state variable. So these variables, it defines the current state of the system. So for instance, FPS, it would control how often the game updates per second. One block size defines the size of the one grid cell in the map. Then lives and score track the player progress. And the boolean flags control which screen is active. For instance, if my start screen should be active, then my boolean flag would just switch to true. So this approach is known as state-based rendering and is fundamental in game engines, mobile apps, and web applications. Next, let's discuss this. Till here, row slice. So that's your map definition. So this two-dimensional array, it defines the entire maze. So each number it represents a type of tile. For instance, 1 is equal to wall, 2 is equal to food, 0 is equal to empty space, and 3 is equal to food is already eaten. And I'll also show you a sample image for this. Here you go. So basically, the entire world is built from this grid, and the movement, collisions, and rendering it all depend on reading this data structure. We create a copy of the original map so that the game it can be reset when restarting. Next, uh, we'll discuss this block. So this is your entity creation. So these functions they instantiate the player and the enemy objects. This separates the object creation from the game logic, which improves the maintainability and enables the easy restarts. Then let's just go down. So let's just move down to this. Now after our entity creation, this function it draws the opening UI, and nothing happens in the game until the player presses the space key. This demonstrates the event driven state transitions, which is a concept used in professional UI and game substance. And after this, you have your game over and quit states. So I'll just go down there. As you can see over here, so these functions they handle the end of the game experience. Instead of reloading the page, the system simply switches state and draws a new overlay. So this makes the game more efficient and provides a smooth user experience. And then you also have a window add event listener option over here. So this event listener it captures the user input such that movement keys, chain direction variables, and space it starts the game. R is for the restart, Q is for the quit. And notice that the input it doesn't directly move the Pacman. Instead, movement is applied during the next update cycle, ensuring consistent physics. Now after that we have successfully went through the game.js file, which is our core engine of this game. Now let's go over to our pacman.js file, which is our file number 3, which is also known as the player engine. So now this class, it would initialize the Pac-Man's position, size, speed, and animation state. An interval updates the animation frame every 100 milliseconds, producing the mouth opening motion. So this is a simple but effective sprite animation system. Now we will discuss this block, which is a move process. So this function executes every frame. It attempts movement, check collisions, and reverts if movement is invalid, and this creates realistic movement constrained by walls. And now you have your eating logic over here. So this function checks whether the Pac-Man is on a tile containing food. If so, it removes the food from the map and increments the score. This tightly couples visual changes with underlying data, an essential principle of the game logic. Now after that you have uh, your move forward function over here. You also have your move backward function over here. Then it's you have your check collision function over here. Now for the check ghost collision function, this function checks whether Pac-Man is on a tile containing food. So for our ghost collision function over here, this function checks if Pac-Man shares a grid cell with any ghost, and if a collision is detected, the engine it reduces a life and resets position. And then you have your chain direction if possible function over here. Now let's just proceed to our file number 4, which is ghost.js. So let's discuss this is in range. So each ghost it measures a distance from the Pacman. If the Pacman is close, the ghost switches to chase mode, and if not, it navigates towards a random target. This introduces behavior based artificial intelligence. Now we will discuss about this function, that is calculate new direction. So, this function implements the pathfinding. The ghost explores the grid to determine the shortest path to its target, and this is a simplified form of the algorithm that is used in robotics, GPS navigation, and autonomous systems. Then you have your check collisions function over here. So this function, it checks all four corners of the ghost bounding box against the map, and if a wall is detected, the movement is reversed. This ensures physical correctness and prevents the ghost from crossing the walls. And that's it. That's actually the whole logic of our Pacman game. Now I'll just switch to my game again and I'll press R. So you have now reverse engineered a complete interactive system. You now understand how game loop works, how grid based worlds are built, how collision detection is implemented, how artificial intelligence navigates space, and how UI states control experience. So these are not just gaming concepts, these are the core system that design principles used in simulations, robotics, and modern software engineering. And at NIIT, our goal is not just to teach syntax, our goal is to help you understand how real systems are designed, structured, and scaled. So, if this session helped you think like an engineer, explore our learning programs in software development, data science, and AI. Until next time, keep building, keep experimenting, and keep learning with NIIT.